Awesome. So it's about 2 o'clock, so I'll go ahead and get started. Seems like there's some students who will be joining just a little bit late, but that's okay. So let's go ahead to the first problem here. So here we're shown how we can prove De Morgan's law in Boolean algebra so that A times B complement is equal to A complement plus B complement. And in order to do this with Boolean algebra, we just have to verify that these two properties are true. And once we verify that these two properties are true, then we will have proven that Morgan's law is true. And so remember that we're asked to do this in Boolean algebra, and that we have this relationship between the properties we learned about with sets, and then how those relate to Boolean algebra with this table of rules that we can use. So remember that for sets, there's a Boolean algebra equivalent for all of these statements. So we have for union, that's the same as or with the plus symbol. Intersections, same as times the and. And then we have the universal, I guess we have complement, which would be negation with the same symbol. We have the universal set, and the Boolean algebra equivalent is 1. And then there's the empty set, and its equivalent is 0. And so by using these equivalences, we can use all of the same theorems that we learned with sets and apply them to Boolean algebra for this more kind of general setting. So if you want, and just take a minute or two to get started on these problems. So showing that A and B, or A complement or B complement, is 1, and then showing that A and B and A complement or B complement is equal to 0. And then we'll go ahead and go over the solutions after about 2 minutes. Okay, so hopefully that was enough time to get at least a little bit started on this first part. So let's go ahead and go through that. So proving the first part, we need to show that A and B, or not A or not B, is equal to 1. So does anyone have any suggestions for where we could start with this problem? So you can just type in chat what properties we should use first, or if you just want to raise your hand and just kind of state which properties you use first. So the first kind of idea here that we can use is what we want to be able to do, right? Is we maybe have this kind of sense of intuition that at some point we want to kind of combine these A and A knots and these B and B knots together so that we can get those to be one, right? We want to use the rule that lets us show that A or A naught. So the negation rule is equivalent to A or not A is 1, using the table that we showed on the other slide to show our equivalences between the sets and Boolean algebra. So we might have this intuition that we want to end up using this property, right? Because we see these A's, not A's, B's, and not B's. And then by using that combination, we can get 1. And so the trick at the start is that, well, we might want to use the distributive law here with the OR version, that A or B and C, and then we can start distributing out some of these variables. Is kind of the intuition here. So if we start here, in order to apply that law, we need to first use commutative. And then now we see that we can use the distributive version, that A or B and C is A or B times A or C. And so now we can apply that. So now with A, not A or not B, or A and not A or not B, or B. Just by applying the distributive law. Here, when we're plugging in, this is representing our variable A up here in the law. And then we've got the B and C here. And then now that we've done this distributive, does anybody have any suggestions on where we could go from here? Yeah, so somebody said associative. Yeah, perfect. That's the idea. Yeah, we want to be able to put the A's together. So the first thing we need to do, associative allows us to rearrange the parentheses, is we're going to need to use commutative first. And then, yeah, we can do exactly like you're thinking and use the associative property. So we apply commutative, so we can swap the B, the not B, not A here. And then we want to do the same thing on this side. And actually, we don't need to do the same thing on this side, excuse me, because the B's already near each other. And then, yeah, now we can use associative. So we've got not B or not A or not A. And then we can do the same thing here with our not A or not B or B. And then can somebody tell me what's the next property we're going to use? So not quite commutative here, definitely a good idea. But there's something that'll make this, that allows us to reduce this equation to a much simpler one. We kind of talked about our intuition at the start. So what rule will allow us to really simplify this equation here? Yeah, so somebody says negation, and yeah, that's going to be the rule, because negation allows us to make this substitution that A or not A. Oh yeah, excuse me, yeah, we do need to use commutative. So somebody did say commutative. Yeah, we do need to use commutative first in order to apply negation. And then, yeah, we'll apply negation. because whenever we apply any of these rules, it has to be in the exact order listed. And so the theorem gives us A or not A, but we have not A or A. So we need to swap these around. And then now we can finally use negation and make the substitution of not B or 1 and not A or 1. So now we finally have a much simpler expression. And then any suggestions on what rule we can use now? Yeah, so somebody's suggesting that we could use identity. And that's a close, but identity doesn't actually apply right to this step because identity has an and. So if this was A and 1, then we can make that substitution. Yeah, so somebody said universal bound, and that's going to be the one for this OR case. And universal bound, that tells us that A or so in Boolean algebra, its equivalent would be A or 1 is equal to 1. So we can make the substitution. So this is 1 and 1. And then what would be the final property we could cite to finish the proof? So the property that shows us that something and 1 can be 1. So this one's a little trickier to see, but somebody mentioned it earlier. It's so somebody's saying universal bound again. Universal bound won't work here because it's using an OR. Yeah, so somebody said identity, and that's going to be the one. Because its equivalent is A and 1 is equal to 1. So in this case, the A is just 1 here. And so this is just equal to 1 by identity. So any questions on this portion? So somebody asked if we could say idempotent as well for the final step. Yes, yes, that also would have worked. So what they're saying is we could have used this rule, which says that A and A is equal to A. And that also would have worked. Yeah, so there's definitely several ways that you can do these Boolean algebra proofs using different properties. There's not just one right way to do these proofs. The thing you just want to make sure is that you're always citing the properties with in the exact order that they're given. Because sometimes it's easy to forget to have to do commutative before you cite some of these properties. Yeah, any other questions? Awesome. So then that's one part of this problem. And then the other portion that we needed to show is we need to show this version where A and B and not A or not B is equal to 0. And the proof for this actually works out very similarly to the previous one. So it'll be nearly identical steps using distributive, commutative, negation, universal bound, and identity rules. It'll work out very similar. So I think this would be a great one for y'all if you want some more practice to work on this one. But just in the interest of time, so that way we could get onto some more of the functions that we've been learning this week, I'll go ahead and move on, but I'll post the solution to this one as well if you want to check your solution and get some practice on this. When I post the slides, I'll have the solution for this problem in there as well, if that works with anyone, unless anybody wanted to see any more specific Boolean algebra proofs. Awesome, I think that's okay. So we'll go ahead and we'll start moving on to some of the functions that we've been learning about. So functions and relations. So this first one, we've got this relation here, and it's some practice in drawing some of the arrow diagrams that we've been working with. So we want to draw a two-set arrow diagram for the relation R, which is defined as follows. So the domain for this is we have the power set of the set 1, 2, 4, 8. And then for the codomain, we're looking at this set B, so that has all the numbers from 0 to 15. And then the rule that we're looking at is S comma N is in the relation if N is the sum of all of the elements that are inside of S. So first, let's go ahead and just work out all of the value. So yeah, if you just want to go ahead and take a couple minutes to start on this problem. So remember, for the arrow diagrams, we want to kind of map all of the elements of the domain to elements of the codomain. So I'll just get you started, and then you can spend some time on it. So for example, in the power set, one of the elements that we have in our domain would be the empty set. And then if we apply the rule, the empty set would be mapped to 0, because 0 would be the sum of the elements in the empty set. So there's nothing, so the sum we just defined to be 0. And so then if you just want to take a couple of minutes to work through the rest of the elements of the domain and how we can map those to the codomain. Right, so let's go through the rest of this problem. So does somebody want to just raise their hand and kind of talk through the mapping that we have from the domain to the codomain for this problem? Okay, so for the domain, right, we're looking at all of the power sets. So let's go ahead and write down all the elements that are going to be in our domain. So we've got the empty set. We'll have the set containing 1, set containing 2, set containing 4, set containing 8, then we'll set containing 1, 2, 1, 4, 1, 8, 2, 4, 2, 8, 4, 8, set 1, 2, 4, set 1, 2, 8, set 1, 4, 8, set 2, 4, 8, and then the set containing 1, 2, 4, and 8. And those will be all the elements of our power set. Those are all the possible subsets of the set 1, 2, 3, 1, 2, 4, 8. And then we just need to map those to our codomain. So our codomain will have the values 1, 2, 3, 4, 5, up to 15. And then, so 1, if we just apply the mapping, so the sum of the elements in this is 1. Sum of elements in the set containing 2 is just 2. Sum of the elements in set containing 4 is 4. Sum for the set 8 is 8. For the set containing 1, 2, the sum is 3. 1, 4, the sum is 5. 1, 8, the sum is 9. 2, 4, the sum is 6. 2, 8, the sum is 10. 4, 8, the sum is 12. This is going to get a little bit messy here. And then 1, 2, 4, sum is 7. 1, 2, 8, the sum is 11. 1, 4, 8, the sum is 13. 2, 4, 8, the sum is 14. And then 1, 2, 4, 8, the sum is 15. So does anybody notice any interesting properties that we have from the mapping of our domain to our codomain with this relation? Yes, perfect. That's what I want. Yes, this is a one-to-one and onto. So this is actually a function. Every element of our domain maps onto one and only one element of the codomain. And it's one-to-one because all elements get mapped. All elements of our domain have a mapping. And then onto because for every element of our codomain, there's some element in our domain that maps onto it. And thus it is invertible as well. So yeah, all of these nice properties happen with this kind of special relation that we've defined. So are there any questions related to this problem with our arrow diagram or how we describe this relation? Awesome. So let's go ahead to the next problem. So we have another arrow diagram problem. And so here we're working with compositions. So we have this function that we define C, and it's from the power set of the set x, y, z, and it maps to the power set of x, y, z. And it's a function defined with this rule so that C of the set A is equal to the set x, y, z, subtracting out all the elements that are in A. And then we define this other function n as a mapping from the power set of x, y, z to an integer in the set 1, 2, 3, or 0, 1, 2, 3. And it's a function like we've kind of previously defined a function n. So it counts all the number of elements that are in this set A. And so what we want to look at first is which composition of functions is properly defined. So is C composed n defined, or is n composed C defined? And remember that when we're using composition, we define composition in this way, so that C composed N is equal to C applying the value of N for some set A. And then when we're looking at N composed C, we're taking the function N and we're applying the value of C from some A. So if everyone just wants to type in chat, which do you think is defined? C composed N or N composed C, or both? Okay, so we have a few who've said N composed C. Do either one of you just want to unmute yourself and kind of explain why that's your reasoning?
So since C maps to the power set of 3 components, then when you plug it into N, you're still able to map it. It takes also a power set with 3 components, and that maps it to something with 4 elements. So the other one won't work, I guess.
Yes, perfect. Yeah, so C takes things that are in the power set and then sends them to the power set. So this output can be sent to the input of N, which takes stuff from the power set to these integer values. But C couldn't take an integer value as an input, right? Because it only takes things that are from the power set. So a kind of way to think about this is like in computer science, right? When we define our functions, we specify what kind of input arguments they can take. If they take integers, if they take strings, if they take Boolean variables. And so this, if we were to have this first one, C composed N, then this function C would be taking in as input an integer, which would be like getting a type error for your function. So that's kind of a way to think about it in a computer sciencey way. But yeah, this is the only one that's defined, and composed C. So now that we have figured out which one of these, okay, yeah, so somebody put in the comment that C's domain, codomain is N's domain, and N's codomain is not C's domain. Yeah, that's definitely a way to think about it. The output of N is not the same as the input for C, but the output for C could be an input for N. Yeah, so that's definitely a way you can think about it with the domain and codomains. So yeah, for the one that is defined, we need to describe the domain, the codomain, and then we need to write an arrow diagram for this function. So let's kind of think about how we can do this for N composed C. And remember, I'll just write the rules again. So N of A counts the number, is the number of elements in A. And then C of A is returning set X, Y, Z, and subtracting out all the elements in A. So when we're dealing with arrow diagrams for compositions, we're going to have to specify kind of 3 things. So first we're going to have the normal input for the function c, the power sets. And then we're going to map those to the power set from the function c. And then we're going to map those to the integers in this set. Since n compose c is just as we went over as n of c of a. So we do c of a first. So we go from the power set to the power set, and then we do the function n from the power set to the integers. So I'll go through one, and then you can take a couple of minutes to go through the other ones, and we'll talk about it at the end. So let's do. So first I'll just write down all the values. So in the power set of x, y, z, we've got the empty set, the set containing x, set containing y, z, set containing xy, set containing xz, set containing yz, and then the set containing lxyz. And then we have the same thing over here. And then finally, we'll be either going to the integer 0, 1, 2, or 3. So let's first go through the empty set. So if we apply the function c to the empty set, where does the empty set get mapped to? So in other words, what is c of the empty set? Yeah, so someone in chat put, yeah, it's the set containing x, y, z. We just follow what c is. So c takes x, y, z, and then it subtracts all the elements in A. The empty set doesn't have any. So you map down here. And then now, where does this element get mapped to? So in other words, where does the function n take this element to? Yeah, it takes it to 3 and just counts the number of elements in the set. So yeah, so if you just want to take about a minute just to finish out the other arrows, and then we'll go through the solution. All right, so if we continue finishing these, we'll take the set x, that'll get mapped to the set containing yz. This get mapped to 2. Y will get mapped to the set containing xz, and that'll get mapped to 2. Z will get mapped to the set containing just xy. This will get mapped to 2. Xy get mapped to the set containing z. That'll get mapped to 1. Xz be the set containing y. That'll get mapped to 1. Yz will get mapped to the set containing x. That'll get mapped to 1. And xyz will get mapped to the empty set. And then that'll just get mapped to 0. So this kind of describes how we could come about finding this arrow diagram. But the only parts that we need, if we're going to kind of finish off this arrow diagram, the only parts we need for this is we need to figure out what the inputs, just what the input is and what the output is. So we could rewrite this omitting this middle step and just showing where the element from the empty set ends up. So the element from the empty set just ends up to 3. So we really just need to describe this side and then its final mapping over to here. But we can use this intermediate so it's easy for us to figure out where those elements go to. So are there any questions on this problem? Anything about arrow diagrams, these functions, or the composition? Awesome. So let's go ahead and move on to the next one. So here we've got this relation, and we'll be drawing another arrow diagram for this. So we've got this set that contains the integers from 0 to 6, and it has this rule that x is related to y if x minus y is divisible by 3. So we need to draw a one-set arrow diagram for R, and then for R compose R. So let's think about drawing the arrow diagram for just the first relation, R. So we'll have 0, 1, 2, 3, 4, 5, 6. And then we're just mapping these elements to the values such that x minus y is divisible by 3. So just by typing in chat, where would the element 0 be mapped to? So what elements such that 0 minus that element will be divisible by 3? Yeah, so somebody said itself, yes. 0 minus 0 is divisible by 3, so that's 1. Yes, and then somebody else said that 3 and 6 also work, so we'll have mapping from here and to here. Something else to note is that 0 minus 3 is divisible by 3, but 3 minus 0 is also divisible by 3. So for both of these actually go in both directions. And then we can figure that out for the other values. So every value will be mapped to itself, right? Because any of these values minus themselves will be 0. And 0 will be divisible by 3. And then we can do a mapping. So 1 and 4, 1 minus 4 will be negative 3, and 4 minus 1 will be 3. So those will be divisible by 3. 2 and 5 work. And then 3 and 6 also work. And so this would be our arrow diagram for just the relation R. And then we need to think about how we could draw one for R composed R. So can anybody tell me what they think an arrow diagram for R composed R would look like? And is it similar to the arrow diagram that we have drawn for R? So does anyone want to just either type in chat their thoughts, or if you just want to raise your hand and kind of state what you're thinking? Okay, so no thoughts. So maybe let's go ahead and maybe you don't see it quite right away. So let's go ahead and describe what R composed R really is, right? So what it means for say 2 elements x comma y to be an element of R composed R. Well, what does this mean? Well, it means that there exists a Z that's an element of A such that X minus C is divisible by 3. And since this is a composition, it also means that Z minus Y is divisible by 3. It's what it means to be inside this relation R compose R. So based on looking at, for this, there's some integer Z such that X minus Z is divisible by 3, and then Z minus Y is divisible by 3. Would there be some similarities between the arrow diagram, if you're looking at the mapping of values in R compose R, to just the arrow diagram we have for R itself? Anyone have any ideas? Yeah, so somebody asks the question, are they the same? Yeah, so yeah, they actually are the same. And let's think about why. So for example, if we looked at kind of, since these are all double arrows, so we could look at if these values are, so let's take a look at, is 0, 6 an element of R compose R? So can you find a Z such that X minus C is divisible by 3, and such that Z minus 3 is divisible by 3? So does anyone have what value we could pick for Z such that this holds, such that 0 minus C is divisible by 3, and 6 minus, or excuse me, and C minus 6? Anyone have any ideas for what value could we pick? Yeah, so somebody says we could use 0 works. So it's there. There's plenty of other values too. For any such value, if you think about following this relation R, this relation is just mapping values that are divisible by 3 to other values that are divisible by 3. So we could map 0 to 0, and then 0 can go to 6 in the composition. And then similarly for all the other values, 1 could get mapped to 1, and then it could get mapped to 4. So 1 comma 4 is in the relation. And all of these same properties will hold. And it's primarily because of these, every element's related to itself. And that there's double arrows for all of these. So 0 is related to 3, and 3 is related to 0. And these will be really important properties that we're going to start looking at the next week. So how can we describe relations that have these properties where every element's related to itself, and if X is related to Y, then Y is related to X. So this is kind of a special relation. It might be good to go back to this relation next week after we start learning about what equivalence relations are and what it means for sets to have some special properties. Because this relation right here demonstrates some special properties, and that's why R compose R is actually the same as R. So are there any questions on this problem with these arrow diagrams and then these relations that we described? Awesome, don't see anything. So let's go ahead to the next one. So this one, we're just kind of explaining how composition works in this problem. So we've defined this set A. And A is a set of all students at your school. And then we define this other set B, the set of all sections of a course. And then C is the set of all instructors. And I guess B I should put, that's a set of. And then we have these three relations, these two relations R and S. So X comma Y is in R means that X is enrolled in course Y. And then A comma B is an element of S means that course A is being taught by instructor B. We're trying to find what is the meaning of S compose R. So if you just want to take maybe 30 seconds to kind of think about what this relation means, and then we'll kind of discuss it. So does anyone have any ideas for what the meaning of S compose R could be? If you just want to raise your hand. And then you can kind of just state whatever you think. Or if you just want to type it in chat, that will work as well. Okay, so someone has a guess. So that a teacher teaching the class student X is enrolled in. Yeah, so let's think about this and see if that's right. So remember that S compose R basically means we're going to be taking S and then applying the function R for some whatever variable X. So so R is going to take some variable X so that student X is enrolled into a course Y. So we can kind of think of this as taking this, then now we're going to have some course Y. And then S is going to take this course to some instructor B. So then we'd return in it some instructor B. So yeah, so it means that X comma Y is an element of S compose R if student X is in instructor's Y's course. And yeah, you could phrase that as instructor Y is teaching, student is student X. So yeah, so any questions on this one? Awesome. And I'm just going to very, very quickly, just because I wanted to get through just one small part of this next problem, is you've just got this one-to-one proof. So we've got this function f from the reals to the reals with this rule that f of x is equal to x cubed minus 2. And we want to show that it's one-to-one and onto, and then find the inverse. So I'll just quickly go through how we could show that this is one-to-one. So remember, when we want to show something is one-to-one, right, we basically want to show that if the output of a function is the same, the only way for that to happen is if the input of the function had to be the same. So no two inputs map to the same output. So the way to show that is we let x1, x2 be in the reals, be given such that the output is the same. And then we want to show that this only happens. So if the outputs are the same, that means that x1 equals x2 for it to be 1-to-1. So if f of x1 equals x of x, so we have this. Then we can just apply the function. So this is x1 cubed minus 2 equals x2 cubed minus 2. x1 cubed equals x2 cubed. And this means that x1 equals x2. But remember, this is because of odd powers. For even powers, you can't make this conclusion. If x1 squared is equal to x2 squared, you can't conclude that x1 is equal to x2. But so we have then that x1 equals x2. So thus, f is 1-to-1. So just a really quick going through that problem. Any questions there? I recommend that you go through this problem for the onto case, as well as finding the inverse function. It's a pretty good exercise as you're getting started with one-to-one, onto, and inverses. And then there's some other problems in the discussion that were just some extra problems that are definitely useful going through if you have any questions. So if you want to see more, there's some applications of one-to-one, and then there's some other problems on arrow diagrams, as well as this important one on set composition. So definitely recommend going through those. And if you have questions on those, please stop by office hours and we can kind of go over those. So any questions before we go? Awesome, I don't see anything. So you're all free to go. Thanks for attending discussion today. I hope you all have a good rest of your day.